You probably should have just gone ahead and ate it instead of. Yeah.
Oh, no, that's right.
Okay, so it should be recording. So 6-3, I hope everything is recording. I have a lot of different things. He's going to come talk to us right now, isn't he?
Did you get 6-1 and 6-2 recorded?
Yeah.
Okay.
And I finally got them uploaded, but our computer was weird, so it didn't work for a while.
Well, I didn't do any homework over there.
I didn't plan on you doing that.
So
I knew that was going to happen. Okay. Where'd my mousey deal go? Okay, so we're going to do the central limit theorem. And basically, okay, I have to find where my mouse is, because, okay. So, in addition to knowing how individual data values vary about the mean for a population, statisticians are interested in knowing how the means of samples of the same size vary about the population mean. So that would be like, hey, I'm going to take you two, and then I'm going to take us two, and then we're going to do stuff like that, okay? So it's kind of something along those lines. So it's how do these different population means actually value, or sample means really. Okay, a sampling distribution of sample means. Sounds crazy and long, but a sampling distribution of sample means is what we're going to be doing. So is a distribution obtained by the means computed from the random samples. So that would have been like, okay, I'm going to take you guys' group, this group, and I'm going to find those means for each individual thing. What happens with those individual means? Okay, so that's kind of what we're thinking about. And those actually also, all those little individual means are going to follow a normal distribution as well. Okay, so the next little piece of that is a sampling error is the difference between a sampling measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. So if I just did you two, it would be like, okay, are you male or female? You guys would both be female. That's going to skew that data a little bit. Okay, it's a bad example because we don't use this tiny amount of people very often because we end up with that bad data. Mm-hmm. Okay, and we usually try to use about 30 people in each sample that we take. Did you get that? I thought you had. Okay. The property of the distribution of sample means. The mean of the sample means will be the same as the population mean. Okay, does that kind of make sense? So I might have, I'm going to try, let me see if my pen will work. No, I was having problems. That's what I asked Mr. Reed to come fix it. Okay, so normally I'm thinking about, okay, I have like all these little tiny people in here that fill up all my little distributions. And I had to sample bazillions of people to figure out this amount of data. Okay, whatever happened. Oh my God, Kat. I know you're excited.
I'm sorry.
Okay. I sampled all these little tiny people in here, and there was a lot of people in this middle area, and there was some out here. And I had to sample all these random people to figure out this area. Okay, so I found the mean. Well, I didn't really want to base everything on a study that I said I'm going to sample 1,000 people, and I hope I get good data. But I'm still going to sample maybe the same amount of people. But what I'm going to do instead is I'm going to make lots of little samples. Okay. And then I'm going to find all those different little means. And hey, if I look at it, so this is a very bad visual representation, but it's still, okay. You want to share it with our video?
I got 59 on my physics test.
Oh yeah, that's bad.
Oh yeah, that's bad.
Okay, so now it's like, oh, hey, look, let's average all these guys together. So let's add these up and divide and find that mean as well. Okay, bad. I wouldn't count on that picture being like the correct representation or anything. But that's kind of what I think of in my head when I see this going on.
Hey, did you grade our test? No? Okay, I just wanted to know so I could see it.
The standard deviation of the sample means will be smaller than the standard deviation of the population. Okay, so standard deviation of sample is smaller than the population one, and will be equal to the population standard deviation divided by the square root of the sample size. So we'll actually have a formula for that. Okay, so we have this, if I kind of think about it in terms of my really bad picture here, is that, okay, this deviates probably like this much, right? Like that's whatever that looks like a normal deviation. But then if I think about it in terms of my little tiny population, okay, this is my standard deviation for this guy, but that's a lot smaller if I kind of think about it like that. This guy, okay, let's call that like 2 inches or whatever, whatever, blah, blah, blahs we're thinking about. But this might only be a piece of that, so this looks like it could be 1 compared to that, okay? But actually how it's related to the original thing is that it is the square root divided by the square root. So this one in case is just like divided by half. So I'll show you what that looks like in a formula. Maybe, is this gonna pop up for the next thing? It's not gonna pop up for a second. Okay, I have it on there. As the sample size increases, the shape of the distribution of sample means taken with replacement from a population, with mean mu and standard deviation sigma will approach a normal distribution. So it gets closer and closer to a normal distribution. Okay, so really kind of, let me give you like a different visual representation. Can you see that one there?
Yeah.
Okay, so if I have a sample, okay, this is still my mean for my sample. I'm gonna write sample down here. Okay, but then my standard deviation is just smaller. So this is still my standard deviation, but it's smaller than, in our case we call it S because it's a sample standard deviation. But when I think about it then, how it's related to my sigma is that it's my sigma of my total population divided by the square root of n. This, I'll give you that in a couple seconds too. So I'm recording right now. If you.
It's working?
No, my pen's not working. I don't know. I can wait for a little bit, but I don't know. So the mean of the sample means equals the population means. We already kind of said that with my bad picture. Yeah, no. So my pens
I'm gonna take a picture of that.
should be able to click and it won't even do anything. I check the batteries, the light comes on. So what this means, mu of x bar is equal to mu. So the mean of the sample means is equal to the mean of the population. Okay, standard deviation of the sample means is the standard error of the mean. That standard error is going to be the same guy up here. You make me nervous too. Okay, so my standard deviation of the sample is equal to the standard deviation of the mean divided by the square root of n, which is the number of people I basically was sampling. So I kind of wrote that here. So instead of S, they use sigma x bar. It doesn't matter, same thing. Okay, your calculator, if your calculator does it, gives you SX. Okay, did you get that? Sorry.
No, go back.
Sorry, let me find it.
I'm like on the last one.
That's fine.
She would like to be your grandma's to get it back.
Yes.
What did you say?
She lost her cupcakes, yeah.
It was the guy who popped the door open. He's probably still milling around.
We're still pretty sure it's Cody.
Well, he swears he didn't do it.
Then it was Sean.
I would swear I didn't take your cupcake either.
Yeah, that's pretty much it. Okay.
Well, like, he just texted me and asked me if I know who did it yet.
Because it's him. The central limit theorem can be used to answer questions about sample means in the same manner the normal distribution can be used to answer questions about individual values. So we're just going to take a look at all those little tiny pieces so that we can generalize the big piece. Okay? We have to do a different z-value formula. It's not too different, but most of the time we don't necessarily know what the mean of the population of the sample is or the standard deviation of the sample is. You can go through, and if you had actual all the data values, you could be doing that in your calculator. Okay, but we simplify it with this. So generally what's going to happen is you're going to be given the population data. So x bar is just that value we're looking for. I don't know what that is popping up there. Something with a projector. So it thinks there's something going on. Is it going to do anything? No? Weird. So these are generally the values that we actually know. It kind of seems weird when you get into like some upper level calculus stuff. if you ever feel the need to, you can actually see where this thing comes from. It's kind of like that weird formula where we divide by n-1 instead of n, and like from a long time ago. And so just all these weird things happen from a lot of calculus derivations that happen.
I have a question for you. I know we can take out of school people to, like, prom. Can we take out of state people to prom?
They in school somewhere?
Yeah.
Yeah.
Okay, cool.
Okay.
As long as I can get a hold of, or Miss Humphrey can get a hold of someone at their school, you know,
Oh, it's in Virginia, so
that
yeah.
says that they're.
Virginia?
Virginia.
Did
Goes
you
to
miss the
private-
whole?
Yeah, he
we-
goes to a private Christian school.
Did you miss
That's-
this?
No, I walked in at the very end of
Okay.
it.
Was
Okay.
this someone you met out there?
Yeah, he was the winner from Virginia.
That's falling in love pretty quick, yeah.
We're not falling in love, he's just never been to a prom before. And
Really?
they're a private Christian school and they don't have prom. And so I was talking about prom and he's like, you guys have prom? And I was like, yeah. And he's like, I've never been to a prom. And I was like, you could totally probably go to mine.
Okay, you guys ready to do an example?
6:13.
Okay, so AC Nielsen, so they do tons of data collection on like TV ratings, if you ever seen Nielsen ratings. So you see that a lot in tons of stat stuff. Most of the time, like, it's an old kind of thing that people would say what they're watching. We don't have that because basically our stuff now records everything that we do. So they already know what we're watching. We don't have to go take some random survey for it. So they don't really use it a lot anymore. Reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the numbers they watch will be greater than 26.3 hours. Okay, so the 26.3 is what we're trying to find the most of. If you look in your book, it really is just example 613.
Okay.
If you
I
find
get
it,
lazy and I end up reading my
334.
book, then I know exactly
Okay,
what this
there
is
you go.
talking about.
So an average of 25 hours, averages are mu. Okay, hours of television per week, assume the variable is normally distributed, so everything's kind of going to say that. Kind of missed when we're in this chapter, everything in here, even if it doesn't say it, assume it, so we get to use this,
You
all
know,
these
you
tools.
always write that little thing a lot different than they write it, so I'm always like, woman, there's no M in our equation, but
Hey.
that's the little U thing.
Is chapter 6
Sorry.
using this?
Yes, yeah.
Awesome.
So you've
I
done
sort
it
of
before,
remember
right?
it from freshman year.
Okay, so it should be like a U with like that, a
Mhm.
tail on that left side, sorry. I'm lazy. Assume the variable is normally distributed and the standard deviation is 3. That's my sigma. I can write that one at least, right? If 20 children between the ages of 2 and 5, so that's our n. We don't really care about the 2 and 5. That's just telling us where their data's coming from.
And it's just screwing with
And this guy is the
X-bar.
X bar that we're talking about. Okay, so we need to go in, and I guess what all is it asking for? Yep. So we need to go find our z-score. When we think about it on a graph, it's asking about more than something.
I want to find it. What would I look at?
Well, we have to find the z-score first.
Oh.
Okay.
Yeah.
So when we kind of draw it, we think about
Group chat.
our mean. We put our mean on there, which is 25. We put our standard deviation just quickly on there. Just this is 3 apart, this is 3 up. 26.3 is not going to be a full standard deviation away, so we have 26.3. Okay, so now what I need to do is I need to use that new z formula, so different from the one we were using for the last couple sections because we're in a sample, so that's going to be a keyword that you're looking for. So I have 26.3 minus my mean of 25 over my sigma divided by my square root of n. So my sigma was 3 over the square root of n is 20. That's how many people I did. What I would do is I would do this piece in the calculator separately from that one so you don't end up with weird parenthesis junk going on.
0.6292.
0.6292. Okay, and this is after the end of it? Okay, so what I really care about is 0.63 because I need to round that, so 0.63. And now I'm actually using that chart for the z-score stuff.
Okay, I want to find it.
Yep, so it is positive, so make sure you're paying attention to positive or negative.
0.63
So I don't have mine.
is 0.7357.
.7357 to you. Okay, so my probability of whatever happening is what did you say again?
735.
7357. Okay.
So does that mean that probability is less than 1%?
Yes, all probabilities are going to be less than 1% because 1%, 100%. I'm thinking. No, this is going to be about 73.5%.
Oh, really?
But remember how we're thinking about it on the graph? This is the less than piece. So remember I have 100% underneath there. So my 100%, I have to then subtract it whenever I'm trying to find this guy. Okay, so I'm going to do 1 minus 0.7357. And what does that get me to?
0.2643.
0.2643. Okay, so there's a 26% chance that if, what is it even asking about now? Find the probability that the mean of the numbers will be, so there's a 26% chance that the average of these 20 children will be above 26.3. So it's weird to convert it back to that word piece, but try really hard to do that when you're actually writing your answer.
What?
That the average of the 20 children, so the average of the 20 children will be above 26.3 is about 26%. Alright, I think most of their stuff really do round to that.
I feel really lame because the winner from Arizona literally flew back and went straight from the airport to her 2-hour French class, and I was like, nope, I'm
Skipped the
sleeping.
whole day, even though your dad's like, Kat says she's coming to school.
Yeah, I was gonna
That's what
come to
she
school,
said too,
and
actually.
I got, I landed and I had 2 hours of sleep, and I was like, nope, I'm going to bed.
Okay, so we kind of already did that. They got 0.194. So, okay, we're going
What
to
did we
ignore
do wrong?
this and say that Taryn did this
Taryn
original
doesn't know what she's
calculation
talking
wrong.
about.
We're going to blame Taryn. Okay.
Exactly.
So how did you type stuff in wrong? So let's
Yeah,
figure out
I
what we're typing.
Didn't.
You might have. I'm going to say
Oh, that book begs to differ.
26.3 minus 25. So I got 1.3 on top.
Yeah, me too.
And then 3 divided by square root 20 is 0.6708.
Me too. That's what I got. That's
Really?
what I did.
That's weird. Okay, then maybe we'll say that we did it right. No. Okay, I don't know what you did, but I got 0.194.
Well, I went out more decimal places.
I just did the second answer, so I did all the decimal places.
Well, I did all the ones that showed.
Did you use multiplication maybe? 0.63.
No.
I wonder if you did the 6708 divided by 1.3?
No, I just.
I don't know. I don't know what you did either.
I'll look when I'm
Same
done
process.
with this.
Just wrong.
Yeah,
Very
just wrong. So we'll do another one though.
Yay.
But yeah, so that's weird. So make sure
See,
you're very.
I did 1.3. Oh, I did minus.
Okay,
My bad.
so Kat and Jake, because I've got to tell everybody this so everyone knows, so I can suspend people when I need to. This hadn't been a problem in the high school, but it is a problem in our school. We have a lot of people leaving rocks indoors,
Rocks?
which is a huge safety issue. Okay, so basically, John, you don't leave rocks indoors. If you come across a door that has a rock in it,
Kick the rock.
please kick it out and let me know, or a teacher know, and they can let me know so I can follow up. Not necessarily really to discipline that kid, but to make sure that we don't have an unsafe situation going on.
I thought you meant like they were tracking rocks into
No.
the indoors.
No.
Like in here. I'm
Okay,
like,
let me
seriously,
put it
like
this
you're
way.
afraid of people tripping? Like what is
A rock
this?
or
Okay.
other
But I get
impediment that will stop the door from locking,
it. Sorry.
okay?
Maybe
And
it was like Hansel and Gretel and someone like left a trail of
That's what
rocks.
I
And
was
even if it's like a
thinking.
weekend thing and you need the doors open, get a hold of me or Kara or Mrs. Humphrey, because we can open doors from our phones.
Yeah.
No
So,
way.
It's pretty cool.
We're supposed
They
to.
just they won't give us that capability.
Because you're lame.
Agreed. All right, I'll be back and look at that sometime.
Okay.
I know I'm just on the top.
I don't know if it actually paused recording, but let me try again. So, oh. No, I clicked resume recording, so it didn't stop.
Even though we're pretty sure that the winners from Minnesota and the winner from Nebraska are gonna get married.
Why is that?
Cause they were all lovey-dovey the whole week, like they were holding hands and
Really?
all that jazz. Yeah, even though it said like no PDA, and you know they were all like holding hands on the bus. And
That's weird to like.
So we're like
get there
pretty.
that so fast.
And we
you
made
know?
the rule that like if two of the winners get married, they have to invite like all the other winners back to their weddings, so that way we can have like a big reunion.
Are you guys all going at the same time in June or July?
We're all supposed to, but not all of them are going. Like the winner from the winner, he was from Florida and his name was Grayson. I don't think he's gonna be there. And then George from Virginia, I don't think he's gonna be there. And then there were a couple other people that it just sounds like they had like family stuff that week, so they weren't gonna be able to. And like New Mexico, her name's Lydia. She was a national finalist for some like women in something program, women in leadership or something like that. And so that's the same week as that, so she won't be there.
That kind of sucks.
Yeah.
Okay, so this is example 614. So the average age of a vehicle registered in the United States is 8 years. That's my mean. I'll try to make it better for Taryn. I'm not clicking with this very good. Okay, so assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that their means will be between 90 and 100 months. So back to math for a second. Okay, so draw my quick graph. My average is 96. I'm looking for it when it's between 90 and 100. So I go in, find my z-scores for each one of those things. So anytime you have your in, make sure you're using this sample z-score formula. So I have z equals my, where is it, 90. So I'm going to do 90 first. So 90 minus my mean of 96. So that one's going to get us our negative number. I guess I'll check all your calculations this time too. So I'll have 16 divided by square root of 36. So that number at least works out nicely. We will do the same junk for 100. So I'll have 100 minus 96 over 16. I'm just going to write times 6 because we can tell what the square root of 36 is. Okay, so I'm going to have 90 minus 96. Don't necessarily have to write it down when you're doing it by yourself, but I like doing those pieces separately. So 16 times 6 over 96. That's really tiny. Negative 6 over 96. Nope, I did a minus. Negative 6 divided by 96 is equal to negative 0.0625. We're going to round that to 0.06. Was that you guys or me?
I think that was yours.
Somebody wants to add me to Skype. That's weird. No, I don't know you. 100 minus 96 is 4
Maybe
over
it's
96.
like a long lost friend from college and they want to reconnect.
No. Your name is Alyssa?
Nice. Your
This guy.
name is Alyssa.
04167.
On the
I'm gonna
internet it
round
is.
that. I'm gonna round that to. I think that's what it said.
Yeah, you go, girl. You lift that little pink weight.
That's great. I was showing my grandpa the swap faces thing.
I
It's
need
so
to do
funny.
that. We were gonna do that and then we never did. A bunch of other people did the face swap and it was funny.
Cause you start out fat and then when you open your mouth, they like work out and then your face like.
They did a face
and
swap of Chris and Chris.
0.04.
And the one Chris was from Hawaii and is like
Dark.
him and his sister are so smart. His sister got a 2400 on the ACT and he got a 20, or not the ACT, the SAT. He got a 2350 on the SAT and a 36 on the ACT.
Impressive.
I was just like, and he's like, cause he told, who did he tell? He told the winner from Georgia that. And he's like, well, that's not that great. And he's like, how is it not that great? And he's like, well, my sister got a 2400 on the SAT. And when he was like, and your point is, like, you aced the ACT.
Mhm. Yeah, no, you rock right there. Okay, so negative 0.06, make sure you're using this left-hand side. 0, 0, so I had to find the 0, 0 over to the 6, 4761, so my probability is 0.4761. You can actually make sure you're writing out those 4 decimal places, 0, 4. So I go 0, 0, 4, 5160. Okay, so what those told us when we're doing that, the first number we found this probability. The second number we found this whole probability. So then we're subtracting the little one from the big one. So 5160 minus 4761. Get your decimal places in there. Did you do that yet? Or you're tired because we don't trust you with a calculator?
0.1, 0.1516.
Point what?
Yeah, this is why we don't trust you with nice
I
things.
said 0.5160.
You started with a 0.151.
Yeah, well,
Yeah, this is, no.
I fixed it. 0.0399.
Okay, good. I got that too, so we can check that.
I already had that
So-
one too.
So there's about a 4% chance that it's.
400 minus 1. How easy is that? Subtracting those numbers.
And I'll subtract.
5160 minus 4760 is 400. Minus 1, so it's 399.
I don't
calculator
subtract
then.
in my head. I
can't
subtract
do
really
it.
terribly in my head.
I actually do it better mentally than I do writing it, so I write so slow.
Oh yeah, I don't like writing it either.
So I
I
get
just
numbers
don't like doing
wrong.
it. Okay, so about 4% that it's between whatever it is that we're talking about vehicles between 90 and 100.
Should you just move the decimal places over 2 spots?
Times by 100 is what you do.
That moves it over twice.
Would
Same
you
thing.
Look at that.
Okay. They said, so this is another weird rule in here that you can't really read. Since the sample is 30 or larger, the normality assumption, so it doesn't have to even say it. Anything that's going to be basically above that 30 for my n is going to have a nice normal curve.
Is that it? Is that it? No.
Um,
And then I also felt really stupid.
did I find these numbers?
No.
What is up with this?
Ooh, who was wrong this time, girl?
Yeah.
Not me.
How? What did we do? I still have it written there, so I have 90 minus 96. What are they doing?
Can we just not do this lesson
Did
then?
you
Well-
minus 2 instead of...
Or can our answers just be permanently different than the books?
I don't know. Maybe they're.
over?
Oh, I totally know exactly what I did wrong.
You didn't
I
do
thought
the
that was
square root of
when I
32.
said that was a big number. I was serious that was a big number. That should have been division.
Okay, so.
Okay. Wow. Okay. You want to try it again? You just make me
No.
nervous, I guess.
I didn't mess up.
Okay. You didn't. Nice.
Only one I wasn't
I also
Okay, so I
felt-
have 16 divided by 6. Okay, again, this is not something you're usually writing down. You just are
Well,
kind of
Point-
looking at it.
Wow.
So 2.67. Okay.
Now I get to
Wow.
start all over.
Yeah, we did get to start over. I'm gonna make you finish that one since we did basically the same thing on the last one though. Okay, so make sure you can find everything. After
Is
you,
that 2.67 or
Yeah.
negative 2.67? No. just
Positive,
2.67.
yeah. So I have -6.
Negative 2.25.
Yay, we get the same thing.
I was like, did somebody check that?
I know.
Hey.
I know, we're just gonna start looking at the answers when we start, okay? 4 over that, okay, that makes way more sense. I thought that was weird, but I'm like, okay, whatever.
Okay, so I'm just gonna
Negative
cross out all these
1.5.
answers.
Okay. Alright, so then we're ignoring these random answers that we came up with. And can you find 9322? So I think the first day, Kat, we just basically practiced. Okay, can we actually find 9322?
Okay, so I did this like a lot.
Yeah, this is what we did a lot your freshman year, I think. So wherever negative 2.25.
I think I'll probably watch those videos tonight and do the
I get
homework.
that number. Cool. 1.5. Yay, I can find that number. So just be careful that you can find those numbers.
Okay.
Okay, they subtract it for us. What is the last example? 615. Let me look at that guy. It is
Oh, we're still
not really any different. No.
Okay. Are we done?
Let me skip that example.
Elbow.
Maybe. Okay, so we have a formula for standard error of the mean. So let me skip it on that thing too. Okay, the formula is accurate when the samples are drawn with replacement or drawn without replacement for a very large number. So the two kind of things that are going on is if they say with replacement, then you're happy and you don't care either way. If they say without replacement, you hope that it's a very large. Usually when we're thinking very large numbers for samples, like over 100 or something like that. Infinite populations, if we're talking about random rabbit populations, those kind of, we just think about those going on forever.
Dude, my internal
Okay.
clock's still off.
Those weird correction factors we're gonna have, so that square root of n was one of them that we kind of had, is necessary for computing the standard error of the mean for samples drawn without replacement for a finite population. Okay, so when this happens, when that second one happens, we have this weird correction factor that we're gonna add to the bottom. By add, I mean multiply. Okay, n is the population size, n is the sample size.
Bye.
I don't know why that was so funny. This is how I talk.
I don't know, I'm really sleep deprived.
I'm sorry. Trying to get that on the same thing. Okay, the standard error of the mean must be multiplied by the correction factor to adjust it for large samples taken from a small thingy. Okay, so instead of this guy on our bottom, we're gonna have this whole thing. Okay?
Great.
Yeah.
You better not give us $100.
I wasn't going to,
And that's it?
pretty much. Okay. The standard error for the mean must be adjusted when it's included in the formula for calculating the z-values. Okay, so that's what's going on the bottom.
Can I ask you a question?
No.
Can you wait like 2 minutes?
Yeah.
Yeah, so that's basically it.
Hold on. Hold on.
Yeah, it doesn't even, I don't even have anything else to click.